Hello everyone. Today I am going to present my seminar on the topic Turing machine with complex storage. This helps us understand how more advanced forms of Turing machines can handle complex computational tasks efficiently. Before learning about complex storage, we first need to understand what a basic Turing machine is and why its storage capabilities are limited. Then we will see how different extensions such as multi-tape, multi-track and multi-head Turing machines help overcome these limitations. So let's begin with a brief introduction to the Turing machine. A Turing machine is a mathematical model of computation proposed by Alan Turing in 1936. Although it is not a real machine, it is considered one of the most important concepts in computer science because it helps us understand what problems a computer can solve. A Turing machine consists of an infinite tape that acts as a memory, a read and write head that can move across the tape, and a control unit that decides what action to perform next. The machine reads symbols from the tape, changes them if necessary, moves left or right, and changes its state according to predefined rules. Even today, Turing machines are used as a foundation for studying algorithms, computation, and the limits of computer systems. Now let's look at the basic structure of a Turing machine. A Turing machine mainly consists of four components. The first component is the infinite tape, which is used to store input and intermediate results. The second component is the read or write head. This head can read symbols from the tape, write new symbols, and move either left or right. The third component is a set of states. These states represent the current condition of the machine during computation. The fourth component is the transition function. This function tells the machine what action should be taken when a particular symbol is read in a particular state. Together, these components allow the machine to process information step by step until the computation is completed. Although the basic Turing machine is powerful, it has some practical limitations. The machine contains only one tape and one read or write head. Because of this, whenever it needs information from another location, the head must move back and forth repeatedly across the tape. For simple computations, this is acceptable. However, when the problem becomes larger and more complex, these repeated movements consume a lot of time. For example, if the machine needs to copy a long string from one location to another, it must continuously move between the source and destination positions. As a result, computation becomes slow and inefficient. To solve these problems, researchers introduced more advanced storage mechanisms known as complex storage. Complex storage refers to enhanced storage mechanisms that are added to a Turing machine to improve its performance and efficiency. Instead of relying on a single tape and a single head, these advanced models provide additional resources such as multiple tapes, multiple tracks, or multiple heads. The main objective is to reduce unnecessary tape movement and simplify computations. It is important to note that these models do not increase the theoretical computational power of a Turing machine. They still solve the same class of problems. However, they can solve those problems much more efficiently and with simpler algorithms. There are several important variants of Turing machines that use complex storage. The first type is the multi-tape Turing machine, which uses more than one tape. The second type is the multi-track Turing machine, where a single tape is divided into multiple tracks. The third type is the multi-head Turing machine, which contains multiple read or write heads on the same tape. Another important model is the non-deterministic Turing machine, which can explore multiple computational possibilities simultaneously. Each of these models was developed to make computations more efficient and easier to analyze. The multi-tape Turing machine is one of the most commonly studied extensions of the basic Turing machine. As the name suggests, it contains multiple tapes instead of only one. Each tape has its own read or write head and each head can move independently. Typically, the first tape stores the input while the remaining tapes are used as working storage. Because information can be stored separately on different tapes, the machine does not need to move back and forth continuously on a single tape. This significantly improves efficiency and makes algorithm design much easier. Let's understand the working of a multi-tape Turing machine with a simple example. Suppose the input string is the given string ABBA. The input is initially stored on the first tape. If we want to create a copy of this string, the machine can read symbols from the first tape and simultaneously write them onto the second tape. After the process is completed, both the tapes contain the same string. In a single tape machine, this task would require many additional movements and steps. However, in a multi-tape Turing machine, the operation becomes much simpler and faster because different tapes can be used for different purposes. This is one of the major advantages of complex storage mechanism. Now let's discuss the multi-track Turing machine. In this model, instead of using multiple tapes, a single tape is divided into several tracks. Each cell on the tape can store multiple pieces of information with one symbol on each track. You can think of it like spreadsheet where one row contains several columns of related information. For example, the first track may store the actual input symbols, while the second track can be used to mark whether a symbol has already been processed. Because multiple types of information can be stored in the same tape cell, the machine can access related data more efficiently. This reduces the amount of tape movement required and helps organize data in a more structured manner. The multi-track Turing machine offers several advantages. First, it allows better organization of information because multiple tracks can be used for different purposes. Second, it reduces the need to search through large sections of tape since related information is stored together. Third one is it simplifies many algorithms because temporary data and input data can be maintained side by side. For example, while processing an input string, one track can store the original symbols and another track can keep track of which symbols have already been examined. As a result, computations become easier to manage and often more efficient than in standard single track machine. Another important extension is the multi-head Turing machine. In this model, a single tape is shared by multiple read or write heads. Each head can move independently and access different positions on the tape at the same time. This is useful when the machine needs to compare or process information from different locations simultaneously. Instead of moving one head back and forth repeatedly, multiple heads can directly access the required positions. This helps reduce computation time and makes certain operations more efficient. Although the machine still uses a single tape, the presence of multiple heads greatly improves the speed of accessing information. The main advantage of a multi-head Turing machine is faster data access. Since multiple heads can read different sections of the tape simultaneously, searching and comparison operations become much easier. For example, if we need to compare the first half of a string with the second half, two heads can be positioned at different locations and perform the comparison together. Without multiple heads, a single head machine would need to move repeatedly between the two positions. This saves time and improves overall efficiency. Therefore, multi-head Turing machines are often used in theoretical studies to analyze more efficient computation methods. Now let's move to the non-deterministic Turing machine. Unlike the previous models, this extension is based on the concept of multiple possible choices. In a standard Turing machine, for every state and symbol, there is only one possible action. However, in a non-deterministic Turing machine, there may be several possible actions. The machines can be imagined as exploring all possible paths simultaneously. If at least one path reaches an accepting state, the input is considered accepted. Although such machines are theoretical and not physically implemented in the same way as ordinary computers, they play a very important role in computational complexity theory. Now let's compare the basic Turing machine with Turing machines that use complex storage. The basic Turing machine contains only one tape and one head. which makes computation slower for complex problems. On the other hand, complex storage models provide additional resources such as multiple tapes, multiple tracks, or multiple heads. These additional resources improve efficiency, reduce unnecessary operations, and simplify algorithm design. It is important to remember that all these models have the same theoretical computational power. The difference lies mainly in how efficiently they perform computations. Therefore, complex storage models are preferred when studying advanced computational techniques. The concepts of Turing machine with the complex storage have several important applications. They are widely used in compiler design, where temporary information must be stored and processed efficiently. They are also used in artificial intelligence and language processing research. In computational complexity theory, these models help researchers analyze the resources required to solve different problems. They are useful in algorithm design because they provide a better understanding of efficient computation methods. Even though these machines are theoretical, the ideas behind them influence the design of modern computer systems and algorithms. There are many advantages to using complex storage mechanisms in Turing machines. First, they reduce computation time by minimizing unnecessary tape movements. Second, they provide better organization of data through additional storage structures. Third one is they simplify the design of algorithms and make problem solving easier. They also allow large and complex computations to handle more efficiently. Because of these benefits, complex storage models are widely studied in the field of theoretical computer science. They help us understand how computational systems can be improved and optimized. To conclude, a basic Turing machine is a powerful model of computation, but it has certain limitations due to its simple storage structure. To overcome these limitations, several advanced models have been developed, including multi-tape, multi-track, multi-head, and non-deterministic Turing machines. These models provide more efficient storage and processing mechanisms while maintaining the same computational capabilities. They play a significant role in understanding computational efficiency, algorithm design, and complexity theory. Studying these models help us gain a deeper understanding of how complex computations can be performed more effectively. Thank you for your time and attention. I hope you understand how complex storage mechanisms improve the efficiency of Turing machines. Thank you.